Hi, in this video we're going to dive deep and look into one of the main algorithms behind deep learning, the algorithm of gradient descent. We'll start by looking at a couple of examples of regression problems and then work our way into some of the details of gradient descent and finally apply a gradient descent to one of these problems as an example to see how it works. So let's get started. So I guess one of the hello world regression problems is, or the hello world regression problem is linear regression. Always a good place to start. So here we've got just a collection of data in variables x and y. So we're trying to model some function with input x and output y using this linear model shown here. And I guess the objective here is to optimize our parameters a and b so that this line best fits the data in some way. So this is a very nice problem. It's probably the most studied regression problem, and it has this very nice system of linear equations that you can use to solve it to find the unique solution. And this system is consistent. So yeah, so it's all very nice and analytically solved. So let's now take the next step up and look at a nonlinear example. And this regression problem is probably less well known, called logistic regression. And we'll illustrate this with an example of a car dealer. So we've got this car dealer who sells electric and petrol cars. And we've plotted each of the cars that they've sold over the years, and which ones are petrol and which ones are electric. So we've got all this data, and sort of showing how there's this transition from petrol cars to electric cars, sort of, and I guess sort of the crux of this transition is probably somewhere around years 2017, 2018. This is all data I made up, by the way. So this sort of transition phenomenon can be modeled quite nicely with a logistic sigmoid, which is shown here. So we've got this function which sort of spits out this number from 0 to 1. So you can interpret it as this probability. And if we sort of assume that our data sort of follows this this model, we can sort of optimize this logistic sigmoid to best fit our data. So basically, it's sort of indicating for each year X what the probability that a given customer will buy an electric car is. And again, here we're optimizing parameters a and b. So like I say, this is non-linear regression, so we can't use linear algebra like we did before, but we can still apply some other analytical tools using derivatives such as maximum likelihood estimation, and so on and so forth. But it's fairly nice still, but as you add more layers and look at more and more complicated versions of this logistic regression, analytic methods become much more infeasible. So this is when we resort to methods like gradient descent. So gradient descent is a numerical method, and basically you're trying to optimize this objective function from some high dimensional space to typically one variable. So here I've just plotted an example of a two-dimensional input space with a one-dimensional output, and we've got this sort of loci of minima along this sort of V shape here. So gradient descent is aiming to find what inputs give the smallest output, basically. And on the right here, I've got the contour plot of the same thing. So we've got in the middle here, we've sort of got this loci of minima, and as we get closer to the yellow regions, we're getting further and further away from our optimal parameters. So the idea with gradient descent is you pick some input point and you look at the derivative of your objective function at that point. And for a function like this, the derivative is just a gradient. So you've got a vector pointing in the direction that the function increases, and you can sort of use that to determine which way is up and which way is down. And if you take the negative of that vector, then that sort of points you towards, hopefully towards a local minimum. So that's the idea of gradient descent. So to make that a bit more concrete, let's look at the algorithm. So I guess to start with, you have to choose a bunch of parameters. So first, the learning rate is a parameter which sort of determines how quickly your gradient descent is going to go. So basically, how big each step you're taking is. The size of each step depends on the slope of the function, so the magnitude of the gradient, as well as your learning rate. Of course, like every algorithm, you have to have some halting criterion. You can use sort of step size to determine this, but more commonly it's you just pick some sort of number of steps and you can plot your loss over those steps. And if you can see a nice sort of decreasing loss, then you know that your gradient descent is doing well. And of course, you have to pick an initial starting point in your parameter space. Usually this is just randomly generated. And once you have all of those, you iterate through your n steps. And at each step where we're sitting at sort of parameters theta k, we take the gradient of that and we multiply it by eta, so to control how fast we're moving down the gradient. We negate it, like I explained before, so that we're going towards a minimum, not a maximum. And then that all gets subtracted from our current position to get to our updated new position, which is hopefully closer to a local minimum. So to apply this to regression problems, you need to be able to sort of have some metric to measure basically how badly your model is doing. So if you're given some model F, then we want to sort of be able to look at a particular prediction of that model and see how far it is from its actual labeled output. So with data X and Y, like I had before, you can basically, so we've got each pair Xi, Yi is just one data point, and you can apply your model to Xi to get a prediction and take the difference between that and your true value Yi, and that sort of gives you how far your prediction was from the true value, and then you just take the sum of those squared errors, and that gives you an objective function, which you can then minimize using gradient descent. So let's look at an example. Here we've got that sum of squared errors like I had on the previous slide, and now I've just got the logistic model that I showed you before as our model that we're trying to optimize. So the nice thing about having these two parameters is you can plot it, and here we've got our contour plot with the gradient like before, except this time I've got the negative gradient, so it's actually pointing down towards some minima. Now here I've chosen an initial starting point and taken the first step of gradient descent, which is what this little green line segment is showing. So up in this the top left side of that line segment is our initial starting point, and then this top right is the initial starting point, and bottom left is the new updated point after our first iteration of gradient descent. And the resulting predicted distribution is shown here in green. So this is our predicted probability distribution of a given customer on a given year choosing to buy an electric car, and the red graph is the true distribution that this data was actually sampled from. So taking another step, you can see that the green graph is just gradually getting closer and closer to the true distribution as our gradient descent approaches a local minimum. And here it starts to zigzag, and now it's sort of zoning in on this local minimum. Okay, so just to finish, let's just look at a few of the downsides to using gradient descent. So one of the problems is that if you're getting close to areas where there's a small derivative, then your gradient descent algorithm can be quite slow. And yeah, in particularly when you're getting close to some local minimum, the convergence really slows down quite a bit, particularly for small learning rates. Now, for more complicated models, such as general neural networks, you can have many local minima, and a naive application of gradient descent can often cause it to get stuck in these local minima. So this is where it's important to be very careful when you choose your learning rate. And because basically if your learning rate is too small, then sort of like I was saying before, it can get the convergence can really slow down and so almost come to a stop. But also if you in some suboptimal local minima, then a small learning rate will I guess decrease your chances of getting out of that local minima to a better minimum, to find new better local minima. And on the other hand, if you choose a learning rate that's too large, then you can sort of get phenomena as sort of depicted in this plot here, where our gradient descent sort of just jumps around this local minima and never really converges to it, but because the learning rate's so large, the step size is large, and it basically is just blowing up. So those are a few of the drawbacks of gradient descent, and there are many other approaches and more sophisticated numerical schemes for addressing some of these problems. I'm not going to go into them here, but yeah, that is some, I guess, what a lot of people use in real world applications of neural networks. Having said that, gradient descent is surprisingly good for how simple it is, and for models with lots of parameters, it can still find really yeah, it can still do quite well. So yes, that's about it. Thanks for listening.